feel free to use the reference sheet on the back of your packet or the back of your calendar. You're going to see double angle identities that we can refer to, okay? All right, so number one, root 2 tan x equals 2 sine x. Okay, let's bring everything over to one side first. Now, we're looking at root 2 tan x minus 2 sine x equals 0. Right now, as it stands, looks like there's no GCF that we can factor out, but maybe we can do a little bit of rewrite. What can we do with one of these to make these look more similar to each other? Yeah, let's get that tangent to show sine over cosine. What can we factor out? Sine x, okay. So factor sine x, that means I'm taking a sine x away from each term. Okay, so we can set each piece equal to 0. This looks a little messy here. Is there? Well, I guess we could always work towards solving for cosine. So I think it's okay if we leave it in this form. Okay, so we'll set sine x equal to 0. And we'll set this root 2 over cosine minus 2 equals 0. Okay, just going to do a little bit of cleanup here. Well, I can try to get cosine by itself, right? If I cross multiply, hopefully I can get to something that looks more familiar. So if I cross multiply here, I get 2 cosine x equals root 2. Okay, so this looks more familiar now, right? Okay, so see if you can find the two solutions that's involved with sine x equals 0, and then two solutions involved with where cosine is equal to root 2 over 2. And we're back to being 0 to 2 pi, so there's no need to add the plus 2 pi n from where n is an element of integer. Okay. I'll work out the solutions in a bit. Try number 2. When you get done with 1, number 2 should feel familiar from yesterday. So really, this entire first page should feel pretty familiar. Okay, so I'll work the problems out as you guys try them, but I want you guys to get a head start. Okay, so where's sine of x equal to 0?
0,
0 pi, okay. Where is cosine equal to root 2 over 2? Yeah, first and fourth quadrant, pi over 4 and 7 pi over 4, okay. Okay, number 2. Get tangent squared by itself, take the square root. Okay, can we get that plus or minus 1 over, or square root of 1 over 3 to look more familiar? Mm-hmm. All right, 1 over root 3 is the same thing as root 3 over 3, just so that it makes it a little bit easier to find on the unit circle. Well, actually, 1 over root 3, we should be able to find that, right? You know that 1 over root 3, okay? Variations of what?
Pi over 6.
Yeah, pi over 6, right? All 4 quadrants, right? Plus or minus. Okay, questions with 1 or 2? All right, take a look at 3. What would you do first?
Move cosine.
Good. Yeah, let's not divide, right? If we divide, we potentially are losing a solution. Subtract, right? Subtract cosine, get it equal to 0, GCF, and then go from there. Okay, questions so far? Set both parts equal to 0. Find theta for both cosine theta and the cosine squared theta minus 1. Okay, where's cosine equal to 0? Pi over 2 and 3 pi over 2. Okay. Where's cosine equal to 1 or negative 1? 0 and pi. Right. We don't include 2 pi because 2 pi is not part of our domain. You see there's a parentheses around 2 pi, so just 0 and pi. Okay, take a look at number 4. 5 sine theta minus 2 cosine squared theta equals 1. I mean, this would be good to factor if everything's in terms of one trig function, right? So what could we do here? Anything that we can replace to make it easier to work with? Mm-hmm. Yeah, move the 1 over, and then we can find a replacement for. Yeah, how about just cosine squared theta? The 2, we can distribute it once we make that substitution. Right? But good, yeah, cosine squared theta. We have a Pythagorean identity. Sine squared plus cosine squared equals 1. So if we rearrange it, we can get that cosine squared inserted to be replaced in terms of sine. And there, if everything's in terms of sine, then we can move towards factoring, right? So now that everything's in terms of sine, we can rearrange it and try to get it ready for factoring. Okay, so let's solve an easier problem if you think that if it helps you. All right. Why don't we factor in terms of x, then we can bring sine back in. So star method, if that's the method that you use, you have your A, B, and C value. Multiplies to be A times C. Adds it to be B, and then your A value goes here. All right, so we're trying to find two numbers that multiplies to be -6 and adds up to be 5. What are those two pairs of numbers there? What's that pair of numbers? Needs multiplies to be -6 though. 6 and -1. Yeah, so 2 and 3 does multiply to be 6, but we're not going to be able to get that to get to be 5, at least not with opposite signs. So 6 and -1. Let's double check. 6 times -1 is -6. 6 minus 1 is 5. We know that works. So now we turn our attention to these new fractions that If we can reduce, we try to reduce. 6 over 2 can reduce to be 3, right? The negative 1/2 doesn't reduce, so we can put that down, but we know that that 2 has a better place to go in front of the x. Okay, we factor in terms of x. Now let's bring our original variable back. Let's bring back sine. Okay, we set each parentheses equal to 0 and see what we have. Okay, questions so far? Okay, anything from sine theta equals -3? No, undefined, right? Sine is only going to hover between -1 and 1, so that's outside of our range. No solution for the first equation. Okay, but we do have sine equal to 1/2, right? So where's sine equal to 1/2? Pi over 6. Good, first and second quadrant. Chapter 5?
Yes.
Okay. Okay, no calculators. You can sit. Okay. Okay, look at number 5. Are we okay up this point? Okay. Cosine of 2y equals 1/2. There's two ways of solving this. We'll do the multiple angles later, but right now we have an identity that we can use. So if you look at your identity sheet, there's actually 3 variations. Right, cosine 2 theta can be expanded into either cosine squared minus sine squared, 2 cosine squared minus 1, or 1 minus sine squared. I would say for this instance, we'll try to avoid the cosine squared minus sine squared, right? We don't want to reintroduce a second trig function. So I would say either the 2 cosine squared minus 1 or 1 minus 2 sine squared, right? And I would say maybe the 2 cosine squared theta minus 1 looks easier because the cosine squared is already positive, but I would say the second or third one, they're both going to work. Okay. So double angle expansion. Okay, questions there? So now we just solve it like how we normally would, right? Add the 1, divide the 2. See if we can get it down to something that we recognize. One plus 1/2 is 3/2. Okay, I see a fraction, right? I can think of it as dividing by 2, but if that feels messy, you can also think of it as multiplying both sides by what? By 1/2, right? Dividing by 2 is the same thing as multiplying by 1/2. So if you want to think of it as, okay, I'm just going to just multiply by 1/2. Makes it a little bit easier to look at. Okay, take the square root, plus or minus. Okay, can that turn into something that we recognize? Root 3 over 2. Okay. All the variations of what? 5 or 6, yeah. Questions? Okay, number 6, just a factoring problem. Maybe you want to factor in terms of x and then bring back the tangent. Star method. A times C, 3 times 3 is 9, multiplies to be 9, adds it to be negative 10, 3 and 3. Okay, so can you think of two numbers that multiplies to be 9, but adds up to be a negative 10? Negative 9 and negative 1, okay? Double check that. Negative 1 times negative 9 is positive 9, that works. Negative 9 minus 1 is negative 10, that works. Okay, we turn our attention now to the fractions. If we can reduce, let's reduce. Negative 9 over 3 does reduce to be negative 3. But instead of x and x, because we're having this to be x to the 4th, we'll need to do x squared and x squared. Okay, let's force this unreduced or this fraction, leftover fraction to the front. Okay, don't forget, our purpose is trying to solve for tangent here, so let's bring tangent back into our factored form. Okay, set both parentheses equal to 0. We're going to see quite a few solutions here. See if you can find all of them. Mm-hmm. Okay, so plus or minus root 3 variations of what? Pi over 3, okay. All the variations, right? One over root 3, all the variations of 5 or 6. Oops, sorry. Okay, does anybody still need to look at first page, number 6? Okay. All right, for those of you who are finished, go to the back page. So back page, we're really going to involve expanding out of double angle. So if you look at number 7, we got sine of 2x. We have a double angle expansion for that. So see if you can bring that sine of 2x out of double angle. And then look to bring everything over to one side, factoring like how you normally would. Right, so we're going to try to find a replacement for sine of 2x, for cosine of 2x. Right. If you're working ahead, we're going to skip number 11. 11 is a little messy, so we'll skip that one. But we're just going to try to get through the rest of this page. All right, everybody good here? All right. I think the more difficult one is trying to find an expansion for cosine of 2x because there's 3 variations, and sometimes picking not the correct one, but picking the best one is going to kind of move us a little bit faster through the problem. So we'll talk about how to make that decision. But number 7, there's only one variation. There's only one option for sine of 2x. So just look on your formula sheet there. Sine of 2x expands to be 2 sine x cosine x. Okay, so subtract to the other side, set equal to 0, factor out the GCF. Okay, what's GCF? 2 sine x, okay. All right, first term, we're left with what? Just cosine x. Second term, we're left with just, yeah. All right, set both parts equal to 0. Okay, this is for all values of the variable. So we need to include that statement. Plus 2 pi n, where n is an element of an integer. Yeah.
How do you know when to use a 2 pi n?
Right, good question. If you look at the previous page here, it says solve the equation for the variable on the interval from 0 to 2 pi. So when they give us that restriction, all we need to do is to find values between on the unit circle. But if it says for all values, then it's expanding outside our interval, so we have to include all the possible variations. So. Yeah, basically indicating that all the coterminal angles could act as a solution to these problems. All right. Are we okay? Are we good with 7? Okay, number 8, cosine 2x equals 3 sine x minus 1. We do want to expand that cosine 2x out. We have 3 variations. We have cosine squared minus sine squared. We have 2 cosine squared minus 1. We have 1 minus 2 sine squared. Technically, all of them can help us get to the answer, but I mean, we want to try to move towards our answer in the most efficient way. So look at what else is used in this equation. Okay, what do you think would be the best option for us to choose? Yeah, the 1 minus 2 sine squared, right? Because our equation is already in terms of sine, so if we can just move towards sine and just get everything in terms of one trig function, it'll just be a little faster, right? Otherwise, if you choose another one, you have to make another substitution, get rid of the cosine, and you're just adding an additional step. So look to see what else is available and try to match that trig function with what's used in the problem already. Okay, so does that make sense, right? We want to target like terms as much, or like variables as much as we can. Okay, so cosine 2x gets replaced. Now we can maybe think in terms of moving towards factoring here. Maybe I'll just go ahead and shift everything over to the right side because I know that factoring, my sine squared will come first. I would like my sine squared to be positive, so I'm just going to try to move. If I'm going to move terms anyways, I might as well move so that my first term is positive. It's just easier to factor if my highest degree, my x squared or my sine squared, is positive. -1, so it becomes -2. Hey, if it helps, try to factor in terms of x. Multiplies to be a times c. A times c is 2 and -2, so multiplies to be -4. Adds up to be 3. Okay, so what numbers can we use? What multiplies to be -4 and adds up to be 3? Yeah, -1 and 4. Double check this. 4 times -1 is -4. 4 minus 1 is 3. We go to our fractions. Four over 2 can reduce to be just 2. Push that 2 out in front. And then make sure you bring your trig function back. Okay, number 9. Should feel like number 1. Well, expand first, and then it should look like number 1. But yeah, give number 9 a try. I'll follow up with the steps.
Yes, okay.
Okay, does anybody still need to look at number 8? Again, we're skipping 11. It's 3 more problems, 9, 10, and 12. Okay, GCF. That's what it's sine, yeah. Okay, there's still quite a bit to resolve inside the parentheses, but at least we can set both parts equal to 0. Okay, I want to resolve those two cosines, but it looks like if I cross multiply, at least I can get the denominators to go away, right? So I'll put this over 1. Cross multiply. Right, diagonals, right? 2 cosine x times cosine x equals 1. Continue working with this part here. Cosine squared x equals 1/2. Let's take the square root. And 1 over root 2 is same thing as what? Root 2 over 2. All the variations of pi over 4. All right, 10 is also expanding a double angle. What do you think would be the best one to use for this problem?
2 cosine squared minus 1.
Yeah. Right. I see there's only cosine involved in the equation, so if I just get everything in terms of cosine, it'll just help move us towards our answer a lot faster. Okay, rearrange, factor. cosine equals -1, only one solution, right? Only at what? Pi. And then back to 1/2, first and fourth quadrant. Skip 11, go to 12. Okay, here there's two equal options here. What could we do here? Either what? Yeah, either get sine squared in terms of cosine squared or cosine squared in terms of sine squared, right? It really doesn't matter. We just want to get everything in terms of one trig function, and that way we can combine like terms a lot faster. So I'm just going to decide to choose to convert the sine squared, but if you convert the cosine squared to sine squared, you'll get the same answer, okay? But it really doesn't matter. We know sine squared plus cosine squared equals 1, so sine squared, rearranging it, sine squared will just be 1 minus, right? Sine squared will be 1 minus cosine squared. Okay, bring everything over to one side. Let's go ahead and add the 2 cosine squared over. Okay, what's going to happen here? Cosine of x equals plus or minus root 3. Root 3 is around 1.73. What does that tell us? Undefined, right? It's going to be outside of our cosine curve and sine curve. Okay, let me check your 2 pages.